Good evening, everybody, and welcome to Astronomy on Tap Atlanta! With what quite possibly be our biggest crowd in our almost 3-year history, thank you everybody so much for coming tonight. Please help me welcome a GSU Astronomy PhD candidate, Mahir Patel. Mahir is a rising third-year PhD candidate at Georgia State University in astronomy and physics. In fact, he, along with every single one of our second-year PhD students, passed their qualifying exam, and so he gets to have an uninterrupted process to his PhD. Give him a round of applause. Mahir studies a very special class of clusters of stars. They are called open clusters, big blue stars that he studies and tries to measure their ages with the best optical and infrared telescope on planet Earth, the Center for High Angular Resolution Astronomy, or the CHARA array, run and owned completely by Georgia State University. But today, he will be doing his sequel to the first ever talk that he gave for Astronomy on Tap Atlanta, which was telling us how we got from the Big Bang to present day, the breakfast that you ate this morning. And now he's going to tell us how it will all end from your breakfast this morning to the end of the universe. So without further ado, please, Mahir Patel!
Good evening, everyone. It's a big crowd. Okay, so today we'll be going through, well, not the history this time, because the last talk was talking about the history of the universe. We're talking about the future of the universe, where we'll be doing a speed run from breakfast to the end of the universe, seeing what possibly might lie in the ultimate fate of the universe. Before we actually delve more deeper into that, one thing I do need to make clear, this talk has nothing to do with the movie, The Theory of Everything. It is its own thing, so, because we are literally talking about everything today. So, let's get started. Now, some of y'all might have not attended my previous talk, so we're going to do a pretty quick overview of what we talked about last time. So, what we did was we began all the way from the Big Bang, the very beginning of the universe, until you had breakfast this morning. And to do this, you need some sort of machine that can make us travel through time and space much more easily. How do we do that? The TARDIS. Now, using the TARDIS, I'm able to, we are able to go to all the way to the beginning of the universe, the Big Bang. Imagine this. Every star that you know, every galaxy that you know is confined into one singular tiny point, and boom, there's a bang, the Big Bang. Now, multiple different phases follows through the formation of the universe until we hit breakfast. And we first start off going into the age of leptons. The universe is still very much a baby at this time. It's a hot, dense mess full of a bunch of electrons and positrons and neutrinos everywhere. It is too hot for more complex atoms and stuff like that to form, so it's not really that useful at this time. But let's wait a little bit and let's let the universe cool down. And by a little bit, I mean about 3 minutes, because this leads us to the age of leptons. The universe has now cooled just enough so that these quarks, so quarks were formed during the age of leptons. Quarks are essentially subatomic particles that make up protons and neutrons. Now, the universe was too hot for those protons and for those quarks to stick together to form protons and neutrons, but it has cooled just enough in about 3 minutes that they do become protons and neutrons. But it's still hot enough that nuclear fusion cannot happen, because you want this nuclear fusion to happen if you want stuff like atoms, like hydrogen, helium, etc. And that's what happens at around the 5-minute mark. We enter the age of nucleosynthesis. The universe has cooled just enough that these protons and neutrons combine together to form the central nucleus of atoms, which is pretty awesome. And during this first few minutes of the creation of the universe, all the hydrogen that is currently in the universe was formed during this time, which is pretty impressive if you ask me. And this lasts for about 20 or so minutes until we reach the age of ions. Now, during this age of ions, the electrons weren't able to combine with these nuclei that were created during the age of nucleosynthesis. In order for something to become an atom, these electrons need to kind of get electromagnetically bound to this central nucleus. And this will take some time. So we let the universe cool for a really, really long time, for about 380,000 years. Once we do that, we reach the age of atoms. The universe is now transparent. What do I mean by that? Well, up until this point in time, the universe was essentially opaque. You can't look through anything in the universe. It's like looking through this wall. You can't see beyond it. That's how the universe was for the first 380,000 years. But by the time the age of atoms arrived, the universe became transparent and you were able to see everything. And the beauty of the universe with its stars and galaxies, where you ultimately had breakfast. This is what we talked about in the last talk. And if you're more curious on what exactly happened in much more details, you can scan this QR link right over here. This is a link to the YouTube video that had my entire talk. But watch that later, because right now we're talking about the second part to this talk, what is going to happen towards the end of the universe. So we're going to make the 0-second mark as the time you had breakfast this morning. So everything that I talk about, every time scale that you'll see is referring to as, like, if I say 5 billion years in the future, it's like 5 billion years from today, not from the beginning of the universe, just to make life a little bit easier. Now, you had breakfast this morning when the universe was 0 seconds old, kind of, according to this presentation. So let's begin. There are multiple different theories on how we think the universe will end. I am a fan of 3 specific ones, which I will be talking about today: the Big Crunch, the Big Bounce, and the Big Freeze. Let's start off with the Big Crunch. Not exactly that. But essentially what happens in the Big Crunch is it follows up with what the universe is doing right now. Currently, we have a bunch of galaxies kind of close by together. But over time, these galaxies are going to spread farther and farther away because of something known as dark energy. Dark energy is the driving factor for the accelerated expansion of the universe. But according to the Big Crunch theory, we believe that in about 100 billion years or so, this expansion of the universe will halt until the universe becomes or comes to a standstill. But this is where stuff kind of starts to get a little bit scary for this particular theory, because once this standstill happens, all of these galaxies start combining, coming closer together, beginning a contraction era. And this continues for the next 100 billion years or so until everything confines into one singular point. So what really happens around during this time? What happens to the stars? What happens to the galaxies if the universe is actually contracting? Well, think of it this way. The universe is dark with a bunch of stars like this. Now, typically, stars are a certain color depending on the temperature they are. So the warmer the star, the hotter the star, the brighter the star gets. So a star that's orange or yellow in color, if you were to make this star brighter, it will eventually turn blue and white. That's how color grading works in astronomy. Now, because the universe is contracting, the universe is going to start to heat up. This will cause some of these stars to actually turn blue. And the other stars also tend to go a little bit more brighter. And this becomes more and more problematic as the contraction of the universe continues on. These stars start to come closer and closer together, just like this, which is due to the heat up of the universe, which causes these stars to grow bigger, to grow whiter. Eventually, they will disintegrate or go supernova. The other stars that never really change colors will eventually also start to change colors as well. They will also go bigger. They will also turn whiter. They will also disintegrate until the universe is really, really, really small. in the final seconds of the universe, according to this particular theory, the protons begin to deassemble. Essentially what happens, all the protons, all the neutrons, all the antiprotons, electrons, positrons are being smashed into pieces, into tiny, small quarks that I said earlier, and the universe becomes a hot, dense mess once again. Not really a fun place to live in at this time, if you ask me. And the universe only has a couple of seconds, and essentially what happens is everything that you knew, every galaxy, every solar system, every beer that you ever drank, everything is being confined into one singular, tiny point until there is nothing. That's essentially the end of the universe according to the Big Crunch. The universe will expand and then contract and go into nothing. Kind of sad if you ask me, which is why I'm not really that big of a fan of this theory, but I am more of a fan of something known as the Big Bounce. So this follows essentially the same theory as the Big Crunch. The universe is getting confined to one singular point, but so much energy is being confined to this one single point that eventually the universe goes into another Big Bang, starts forming new galaxies, starts forming more and more stars. It will continue to expand until a certain point down in another timeline until it contracts once again into a tiny point, and the Big Bang will keep continuing again and again in an endless cycle. If this is truly the case, that means in a different universe, I may have already given this talk to y'all, which is kind of cool to think about. But what is my favorite theory of the end of the universe? Well, I believe the end of the universe will go off with the Big Freeze. This has multiple different names. It's also called the Big Freeze. It's called the Lambda CDM model. It's also called the heat death of the universe. I'm going to call it the Big Freeze because I get to do pretty cool slide transitions like that. So, what does this entail? Well, before we actually get into that, I do need to mention a little bit of science that was recently done by a telescope called DESI. DESI is a ground-based telescope here on Earth that is used to study the dark energy in the universe. And recently, it found that the acceleration of the universe, or the dark energy that is the driving force for the acceleration of the universe, is actually weakening over time, which may prove part of the Big Crunch theory to be correct, that the expansion of the universe is going to halt at a certain point down the line. But what this theory entails is that the expansion of the universe will not result in a contraction. Instead, it will expand and kind of stand still for all of eternity. And that's what I'm a big fan of. So we're going to bring back the TARDIS because this is the timeline I believe in, so the TARDIS will go in that timeline because I control it. So, all right, let's talk more about this. Now, before I can let you on into the TARDIS, it's important for y'all to know how the universe works today. Almost all the stars in the universe are born something called a cold molecular cloud, which is essentially a gigantic cloud in deep space that is cold. And this is what is used, like whenever a part of this cloud collapses, this results in the formation of something called a protostar. This is kind of what a protostar looks like. This is not really a real image. That is a real image. That is a artist representation of what it might look like. But essentially what's happening is the protostar, a part of the cloud collapsed and a protostar is formed, but the heat up of this protostar is done due to gravitational contraction. This gravitational contraction heats up the star just enough to then become an actual star. We don't really consider these protostars to be exactly stars. A star is considered to be a star the moment it begins fusing hydrogen into helium in its core. Every single star in the universe has, at one point during its lifetime, fused hydrogen into helium in the core. And this is the case for every single star. When you look up in the sky, all of them have done this at a certain point in time. All of these stars, so the higher the mass of the star, the heavier the elements it's able to fuse. So something like our sun is considered to be a lower mass star. So the sun is currently fusing hydrogen into helium in its core. But if we were to assume something that is much more massive than the sun, let's say something that is 10 times the mass of the sun, it is possible that that star, instead of fusing hydrogen into helium, is possibly fusing even heavier elements like carbon into neon, neon into oxygen, oxygen into silicon, and so on and so forth. So these higher mass stars tend to actually evolve much more faster than these lower mass stars. But the lowest of the low mass stars will last a pretty darn long time, almost in the trillions of years mark. But I mention this because the fate of stars lies into two, most, almost all the stars in the universe will either end as something called a planetary nebula or a supernova explosion. And within this lies two stellar remnants, a white dwarf for the lower mass one, and a neutron star or a black hole for the higher mass stars. Now, I mention this because if we look far, far, far beyond towards like the universe's timeline, all we're going to see are these stellar remnants, these white dwarfs, these neutron stars, and black holes. That's what will remain. This is what the universe looks like today. Over here in this picture, every single speck of light that you see is a galaxy, and each of these galaxies hold hundreds of billions of stars in them. You're essentially seeing quadrillions of stars in this one single picture. And from those stars, most of those stars are something known as red dwarfs. They look like this, kind of. And these red dwarfs, as I said earlier, they're really, really low mass stars. That means that they will last for a very, very long time. We think in the trillions of years scale. So that's pretty cool. There's another fun fact that comes out of this. Almost about 90% of all stars that will ever be born have already been born in the universe. And we know this because the dust and gas has already been used up throughout the universe. It's kind of decelerating at a certain rate. But nonetheless, you're now ready to step into the TARDIS and go farther and farther into the future. How far are we talking? About 1 trillion years into the future. So a really, really long time away. By around this time, our solar system is no more. Our sun is a white dwarf. If humans were still alive during this far away time scale right over here, they would likely be close to some of the red dwarfs because, as I said, these red dwarfs are known to last a couple trillion years. So we probably made home around some of them, which I hope that happens. So, but the universe is much, much more dimmer than it is today. It only consists of these red dwarfs, white dwarfs, neutron stars, and black holes. And that's essentially the entirety of the universe, hence why it's so much dimmer. All of these stars that are within a galaxy is what illuminates a galaxy, essentially. So all the galaxies that you know today, like the spiral galaxies that you see, or the irregular galaxies that you see, they are likely to not exist 1 trillion years down the line because all star formation has now ceased. No new stars are now no longer being formed. And what you're going to be left with is something known as an elliptical galaxy, if that, because there's a big if there. It's likely that even these galaxies do not exist. Elliptical galaxies are the oldest galaxies that we have in the current universe because they have almost no star formation happening in them. So at some point down the line, maybe these also do not exist, which might be around this time. So yeah. Let's go a little bit even more further into the future because we know these red dwarfs last a couple of trillion years. So let's go about 10 trillion years into the future. Now, if we see, the universe is mostly made of just white dwarfs, neutron stars, and black holes. The universe is extremely dim now. There is almost no light. Now, for sure, there are no galaxies anymore. And this is kind of what the universe looks like. It's kind of sad. And humans can no longer live next to those red dwarfs that I talked about. So if they were still alive 10 trillion years down the line, they would probably make their home around something like a white dwarf. But these white dwarfs will also not last forever. Welcome to the black dwarf era. So I'll get the time scale. We're about 1 quadrillion years into the future. So yes, we're going to unimaginable lengths of times away, but about a quadrillion years into the future, the white dwarfs that we know today, they're slowly radiating away heat, slowly but surely. And eventually, all the heat from the white dwarf will be dissipated until what is left to be known as a black dwarf. A black dwarf is essentially just a white dwarf, but with a temperature of nearly absolute zero. Absolute zero is the lowest temperature that can be achieved in the universe. You cannot go lower than absolute zero. These black dwarfs are as close to absolute zero as possible because all the heat from the white dwarf has now radiated away given enough time, hence the quadrillion year mark. So now the universe is truly, truly dark. We cannot see anything. And if there were still humans alive relying on white dwarfs, they really cannot survive anymore. No life can now exist in the universe around this time scale. Also, we can't see anything either, so luckily the TARDIS is equipped with the best flashlight in the entire universe, which allows us to see all of these black dwarfs and the black holes. So that's why we know that these still exist, but in reality you wouldn't be able to see them anyways. But we know a little bit more physics than that, and let's see what actually might happen later down the road, even though humans might not be alive during this time. So, welcome to the one Google year mark. That is 1 followed by 100 0 years away. A very, 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 very long time away. And I'll welcome you to the Hawking era. Now, these black holes that are still there in the universe, they're also slowly away radiating their energy from the black hole itself through something known as Hawking radiation, coined by Stephen Hawking himself. So this Hawking radiation will eventually radiate away the black hole into nothing, really. Nothing will be left once the black hole kind of radiates away all of its energy through Hawking radiation. And this is 1 Google years into the future. Let me try and put this number into perspective because this is a very, 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 very long time. So take this. You're here on Earth. You have a pipette in your hand. Go to one of the oceans, let's say the Atlantic Ocean. Now you're going to use the pipette, take 1 drop from the Atlantic Ocean and put it into a giant bucket. Wait 1 trillion years. Now take a pipette again, take another drop, put it into the bucket. Repeat this whole process until you empty out all of the oceans on the planet, waiting 1 trillion years between every drop of water. Now you're going to go back to your bucket with your pipette, you're going to take a drop from your bucket, put it into the ocean, wait 1 trillion years, and go back to your bucket, take another drop, put it into the ocean until you fill up all the oceans on planet Earth. And now repeat this entire cycle for the number of atoms in the solar system. Not the number of objects, the number of atoms in the solar system. And you would still not be close to that time. You'd be about 10 to the 94 years. Yes, it's an absurdly long time away. I was not exaggerating when I said that. But yeah, eventually in the Google years, all of these black holes will be dissipated to nothing, and only one thing will remain in the universe, the black dwarfs. But this is still not the end, because there's some pretty interesting physics that's happening inside of these black dwarfs as well. Something known as quantum tunneling. Ooh, scary, but it's not that scary. I'll try to explain it. Now, let's say you have a rock on one side of the hill, and you want to take it to the other side of the hill. According to classical physics, the best way to do this is to pull the rock up the hill and roll it back down. But if you were working with quantum mechanists, I guess, you could use quantum tunneling. So this is the same idea that my hand could potentially phase through this wall if I do it a certain number of times for, I don't know, an unimaginable long time. But eventually, my atoms will line perfectly with the atoms in the wall, and my hand would phase through that wall. It's the same concept that happens here. That rock could technically phase through the hill itself through quantum tunneling, given enough tries, given enough time. The same thing is happening inside of these black dwarfs. So inside the black dwarfs, there are a bunch of particles or a bunch of atoms that are kind of bunched together thanks to something known as degeneracy pressure. Stars like our sun is fusing these heavier elements because there's enough heat and there's enough pressure. There is no heat in a black dwarf, so all it's held by is pressure. But this pressure causes these atoms or these molecules, ions that are inside the star to kind of collide with each other and bounce off. But this eventually, given enough time, one of these atoms would possibly quantum tunnel into each other, fusing into heavier and heavier elements. So the inside of a black dwarf is currently mostly just carbon. This carbon would fuse into neon. Eventually, that neon would fuse into oxygen. The oxygen would fuse into silicon. And finally, the silicon would fuse into iron. Once iron is formed inside of a star, you wrote the death certificate of that star. The star will 100% die the moment it starts to fuse hydrogen. And once this happens, a star goes supernova. And the same thing will happen to a black dwarf. A black dwarf won't be able to handle all that, and eventually a supernova will happen. That time scale also crazy, 10 to the 1100 to 10 to the 32,000 years. Remember the whole pipette situation that I said about the oceans? Repeat that for the number of atoms that are in the observable universe, and you'd still only be at 10 to the 200 years. Nowhere close to that 1100 mark, and nowhere remotely close to that 32,000 mark. So this is an insanely long time away. It's unfathomable. Crazy. But eventually, once the last black dwarf will go supernova, all that will be left in the universe is just darkness. Kind of sad, so let's hop on back to our TARDIS and go to the present day. I want to mention something. Do not fret, because the end of the universe, as I just showed you, is quite literally forever away. Thank you.
Thank you, everybody. Does anybody have any questions for Mahir? I was just over there. Go fuck for it.
No, your question makes sense. Do I have an answer for it? Oh.
Have fun, buddy.
The white dwarf realm is white dwarfs. Sorry, you said white holes, correct? Yes, white holes are a completely different can of worms that I do not personally know about, but there's multiple different theories that people think that what they might be potentially leading to different universes. So this could potentially lie with the big bounce theory that I mentioned. Maybe we go back to a different universe, but who knows? This is 100% just me guessing what that might be, but we don't really know. I don't think we've ever really observed a white hole, ever. But it is theoretically possible.
That is correct.
Yeah.
We've never seen a white hole. I prefer, instead of white holes, I prefer the creepy bookcase staring at child Jessica Chastain. But that's just me. I also have a pretty loud voice. Oh, go for it. What piece of information are you looking for to completely, of course you can't completely accept the theory, but to really jump on one of these theories versus the others?
Ooh. So cosmologists 100% work on theory 100%. We are kind of guessing of what might happen. The only thing we can possibly do is keep taking more data, see how the universe behaves over a bunch of period of time. But at this very moment, without much more time looking at the universe, we can't really know for certain what exactly might be the true case. It could be that all of these are just wrong and it's something else. So it could be that the universe just ends in a few billion years. I don't know. But yeah. Yes.
Go ahead.
I can yell too.
Go ahead. I love this. This is great.
So, love the acronym AOT. My second favorite AOT acronym is Arrow of Time.
Oh,
in,
yeah.
In big crunch theories, what's the prevailing thought? Is it that entropy, acts the same way and the arrow of time goes the same direction as it does now, or does it reverse and go in the opposite direction?
Oh. So I think time still continues linearly, even in the big crunch. So it won't reverse. I highly doubt it reverses. But yeah. Yes.
I think you mentioned that the rate of expansion of the universe was slowing, and I've heard previously that it's increasing. Is there consensus on that, or is that?
There's I have looked through multiple different sources. I've seen both stories. I've seen people saying that the universe is accelerating. I've seen people saying that the universe is decelerating. Like this DESI study was saying that dark energy is actually weakening over time, which might suggest that the universe's actual expansion might slow down in the future, which is kind of interesting. So, do we have a solidified answer? No, not at the moment. But hopefully soon, because we do have really cool and really good telescopes now, which helps us look at how the universe is behaving at really, really far away distances.
There was another hand that popped up. Yeah. Up there? Perfect.
In your lifetime, what might you hope for better technology for collecting data to be built?
How much money you got?
um, hmm. Ooh. I think we have enough technology to build whatever we want. I think it's really all about the money. Given an infinite amount of money, we can probably figure out what's really going to happen with the end of the universe, how the universe will actually end. But not a lot of people like to fund astronomy nowadays. Yes, boo.
Yeah, let's finish up there. Go ahead.
Hi, I'm wondering if you saw Project Hail Mary, and if so, how scientifically accurate is it, and what are your thoughts?
I did watch Project Hail Mary, and I'd say it's pretty close. Not the closest movie that I've seen that is as I think the closest movie that I think that's as accurately astronomically possible would probably be Interstellar, right? But Project Hail Mary is pretty darn close. It's pretty good. Would astrophages actually be real? Maybe. If they were, then yeah. But it's a pretty good representation, though. Yeah. Yeah.
Cluster back there. We got some loud voices back here.
I'll try.
Go for it.
What are your thoughts on the Hubble tension?
Ooh. So Hubble tension. That's the.
You can tag off at any time.
I'll tag.
Okay. Science is collaborative. The Hubble tension. The Hubble tension is a measurement, two independent ways to measure how fast the universe is expanding. There's one way to do it where you look at how nearby galaxies, how fast they're moving away from us, and then comparing how fast further galaxies are moving away from us, and we can measure it that way. That's purely observational, and we get one number off of that. The other way to do it is seeing the light that was first created from the universe in the cosmic microwave background radiation. That is a map of where light was emitted and how much light was emitted in the first possible time where the universe could make particles of light. And we take that and we're like, okay, we've got toy universes in our supercomputers, and before we had that benchmark, we were just letting universes evolve with our best guesses and trying to tie them to present day observations as a check to see how good we did. Once we detected the cosmic microwave background, or the CMB, maybe you've heard that acronym, we had another benchmark that was so much sooner in the universe's timeline than relying on galaxies that were near to us. And so we said, okay, let's go into our toy model and let's make sure that that model that's pretending to be the universe hits the same there's a bunch of different little knobs that you can turn to make sure that your universe is behaving physically realistic, meaning like what's the geometry of it, how fast is it expanding, how much matter do you have in there, how much dark matter do you have in there, how much dark energy do you have in there. And the best rate of expansion that we can plug in to create a realistic universe in our simulations, that expansion rate does not agree with the one that we measure observationally. So what is the conclusion of that? Are our observation techniques wrong? Maybe. Is the premier method or theory of the universe, the all-encapsulating theory of the universe, we call it lambda cold dark matter, are pieces of that wrong? Maybe. Is there new physics in the early universe that we have not yet been able to understand? Maybe. It is an extremely active area of astrophysics right now, and a bunch of money is going towards solving that problem, including the funding of the James Webb Space Telescope. So it is extremely active right now, and if you stick around until October, which is our 3rd-year anniversary, you might just hear another talk about it. Okay. I'm seeing a lot of arrows pointing me that way. Let me give you the microphone. Can we pass this back?
Yeah, we're here for her.
Okay.
Hello. So I feel like I'm behind this big bounce theory, and I have been for a while. Could you explain about how does the Big Bang even become a thing if you have something like the Big Crunch where everything turns to nothing? So how do we even have a Big Bang happening from that, and then you have a Big Freeze, which everything turns into nothing again. So it's just like a Big Bang doesn't seem like it even be a possibility in the first place. So.
Yeah.
I'll let you deal with this one, buddy.
Yeah. Okay. So you have a good point, which is probably likely why the big bounce might be the true case. There's arguments that you can make all over the place, but yeah, it would make much more sense if the big bounce was the true end of the universe, because the Big Bang would need to have happened from somewhere. But then the argument would be, how did the first ever iteration of the big bounce occur? Then where did that come from? We don't know. Because as I said, like in the first talk, the universe was kind of opaque until a certain point of time. So we really cannot see what is exactly happening in the very, very beginning of the universe. It's just the universe is simply opaque. We can't look through it. It's like looking through a wall, essentially. That's why we don't really know how the Big Bang actually truly began. We only have theories, hence the Big Bang theory. But yeah, no, that's an awesome question, and I really hope that someday we can figure out the answer, what truly caused the Big Bang to actually bang. Yeah.
Yeah, if you had 24 hours of the James Webb Space Telescope, what would you look at first?
That's a great question.
That's a really good question.
Repeat it just one more time.
So this gentleman asked, if I had 24 hours with the James Webb Telescope, what would I be looking at? I don't study really far away things. I kind of stay close by.
Just say exoplanets.
Exoplanets. There's a lot of things. So personally, the James Webb Telescope is not that useful to me, but it would be useful to someone like Justin right over here who can answer that question.
The easy answer is let's train it on a small sample of the most probable planets that we have detected that have the best ingredients for forming what we believe to be a inhabitable world. That to me is boring. So I would rather do what the president or the director of the Space Telescope Science Institute did in the early 2000s, my favorite era of time, period. And he's like, I want to take the Hubble Space Telescope and I want to just train it on a blank piece of the sky that we've never observed before and just see what's out there, because we didn't really have a handle on how many galaxies existed in the universe until Hubble was launched and after we gave it LASIK surgery to repair its mirrors and such. And everyone's like, you're going to take Hubble Space Telescope time and you're going to stare at a blank piece of the sky? No. And he's like, well, that's a funny story. I'm the director, so that's what we're doing. And that became, if any amateur astronomers or astronomy enthusiasts, that became the Hubble Deep Field Survey, which was a blank piece of the sky. No one had ever looked for it, and he trained the Hubble Space Telescope on that for over 11 days worth of long exposure time. And if y'all don't know, the Hubble Space Telescope is orbiting around the Earth. It takes 90 minutes for it to go once around the Earth. So if you ask for time on Hubble, you're not asking for the amount of time that it takes for you to get a good detection of whatever you want. They ask you, how many orbits would you like? Yes. So it took hundreds of orbits around the Earth to reveal one single image that was, if you put your extend your thumb out and you look at the surface area of your thumbnail, it is smaller than the surface area of your thumbnail, and there were 10,000 galaxies in that little square that Hubble saw with just 11 days of data. So if I had, how much time did you give me? 24 hours. James Webb is bigger and higher resolution than Hubble is. So just do the same exact thing. We've already done it. Do it for something else. Do it for something else. Get the most amount of data possible, because that's what gives us cosmologists and us extragalactic astronomers more data to confirm things that right now we don't have a clear answer on. We can answer more questions with more data as opposed to staring at one planet and be like, oh my god, it has oxygen. Cool. What are we gonna do? Move there? I don't know. Like, all right. Fire away up there.
Hi. Okay. So in your discussion of the end of the universe, you talked a lot of like stars, black holes, and whatnot. But as you've also brought up a few times, dark matter also exists. How does that play into everything, or do we just not know at all because we don't even know what it is?
Yes.
Yeah.
You might have realized that this talk goes on a lot of maybes. Yes, we don't know what dark matter really is, even today. So we do kind of know. So there's two different things. Dark matter is different from dark energy. Dark energy is what's causing the expansion of the universe. We know that that's most likely a thing, but dark matter is still a very iffy subject. It depends on who you're talking to. There's wimps and there's machos, and yeah. Yeah.
Follow up on that actually.
Yeah.
So the big freeze, what kind of confused me is when I hear freeze, you think, oh, it's not accelerating anymore the universe, and you said the dark energy is what drives this acceleration. So when you say there's a big freeze, I'm assuming energy is more evenly distributed. So are we still saying that there's an acceleration in the expansion, or does that also, when you say freeze, does that stop it?
Yeah, the big freeze basically suggests that at a certain point in the universe's history or the future of the universe's expansion is going to halt. So dark matter will no longer be a driving factor. Oh, sorry, dark energy will no longer be a driving factor for the expansion of the universe. It's just going to come to a standstill. Hence, the big freeze is why it's been coined freeze. So essentially, it's saying that dark matter won't be the most dominant source of energy in the dark energy won't be the most dominant source of energy in the entire universe. Is what this theory suggests. Did that clear it?
You still have gravity.
Yeah.
I mean, you still have gravity between these stars. They would eventually pull together.
They're too far away to have any gravitational interaction between these stars, right?
I think.
Yeah. Okay.
I think. Okay. There's the big freeze or the big chill, which is continuous expansion to the point where the average temperature everywhere is so close to absolute zero that you don't have any kinetic energy being achieved anywhere. There was the static universe, which was originally theorized by Einstein when he published the general theory of relativity, where he thought the universe was static, where the amount of outward expansion caused by dark energy would be completely balanced by the inward force of gravity from normal stuff like stars and galaxies and also from dark matter. That is not quite what we observe. We observe the universe to be continuously expanding. There's the third option where you have more mass generating more gravity than there is a force outwards caused by dark energy. And that's, I don't remember if you had this, the big crunch. Yeah, that's where the gravity would be stronger after a certain period of time than dark energy, and so you would get an eventual contraction. So there's three possible scenarios. The one that he was mentioning was the static one, where you would get, on a universe scale, effectively the same thing that you get in stars, where you have fusion that's pushing everything outwards and gravity pulling everything inwards. And because they balance each other, you get a very nice, stable sphere. That's what the universe was theorized to be back, in the early 1900s, and that's not quite what we observe the universe to be doing now. Yeah. Okay, over here.
So towards the end, when to the kinetic energy said that their ending is basically from the tunneling and then eventually supernova, right? So,
Yes.
I mean, the universe is, it's matter and energy, and there's, they go back and forth. But like at this end stage, like, is the mass and the energy like literally gone, or is it just diffused enough to where it doesn't interact? It's effectively, yeah.
Yeah.
The matter and energy go away. Like,
Fantastic question.
Yeah. No, by the time a star becomes a black dwarf, it is practically dead. It's not going to do anything. There is no energy in the star itself. It has radiated away all of its heat. It's just a really, really dense, cold object. It's probably not even a star at that point. It's the same mass as it was. The mass doesn't go anywhere. The mass is still there. It's the same mass that it was as a white dwarf that has radiated away. But there's so much pressure. All these particles are so densely packed inside of a white dwarf that these particles keep on colliding with each other at really small ranges, but they still collide with each other, kind of bounce off. But once in every Google years or so, that it could possibly fuse together to form these heavier elements is essentially how a black dwarf supernova happens. And this term was coined very, very recently, around the 2020s, that a black dwarf supernova is technically possible. Yeah.
so I guess the real question is though, is like the sum of all the mass in the universe stay the same at the end, or is it?
Yeah.
The sum of mass doesn't remain the same. The sum of energy remains the same. The amount of mass that a single white dwarf is going to have is going to shrink very, very, very slowly, but surely over time, because it loses its mass and transfers it back into energy.
So that, but when the energy leaves the black dwarf,
yeah,
where does it go? It still exists, is what you're saying?
It still exists, and it just gets so dispersed.
That it doesn't interact.
Yeah.
Okay, that's what I was getting.
Yeah.
Alrighty, we got a couple more. Let's go back in the corner there, and then we'll work our way forward. Yes, sir.
So at breakfast this morning, the universe was still hospitable to life.
Yes.
Yes.
At the end, it's not.
No.
What is the earliest point in the timeline, let's say of the Big Freeze, since it's your favorite one, what's the earliest point at which the universe becomes completely categorically inhospitable to biological life as we understand it here, carbon-based water, etc.?
The moment all the white dwarfs become black dwarfs. For life to exist, you kind of need some sort of light source or some sort of energy. The energy radiated from black holes is almost impossible to harvest to anything useful. So you can't really use Hawking radiation. These black dwarfs are essentially dead stars. So really, we can't get any energy from anywhere. White dwarfs, you can still grab some of the energy from it because it's radiating away heat. So I believe white dwarfs would be the last possible chance for any life to exist in the entire universe. So about a quadrillion years. Yeah. Yeah, we have some time.
Let's take a couple questions. Let's go right here. Yeah.
Do we have an estimate of when the last new star will have formed?
Ooh. Maybe. I do not know the answer to that though. Ooh. I'll look into that actually. There's probably theories on that 100%.
When the last star is formed?
Yes, because like currently it's like 90% of all stars that will ever be born in the universe have already been born.
Yeah.
Yeah.
So it's relative. It's
close.
Nearer than it is farther. Yeah.
Right. When do new stars stop forming?
The moment gas and dust runs out in the universe. So these stars are born from this gas and dust, and the universe was quite a dusty place in the very beginning, but eventually it will run out. So sooner ish.
Okay.
Yeah.
Alrighty.
Yeah.
Right into the barrel.
Since the James Space Telescope just discovered these red dots with like the black hole stars in them, if that the black hole era will start at the end of the universe, will it be like the stars themselves, or really the black holes themselves will just like eat them and they'll be by themselves?
Ooh, that's an awesome question, and I'll let you answer
Okay.
that. Yeah.
There was a lot in that question right there. Let me unpack that a little bit. Yes, if you were to search James Webb Space Telescope results, you might see a bunch of hits about little red dots. These little red dots are things that the James Webb Space Telescope has seen that Hubble wasn't able to see because James Webb is bigger and it has higher resolution, and we spent $9 billion more of your taxpayer money on that than we did Hubble. So it's worth the money, I promise you. But what it saw is all these little dots. And we took some extra observations to help us know how far they were away. And these things were popping up at 500 million years after the Big Bang, a billion years after the Big Bang. They were happening, they were popping up. Observation, we've seen them. Regardless of what our theory says, we've seen them, we've detected them, they're there. And it sort of was like, these galaxies, according to our theories, should not be popping up here because there hadn't been enough time in the universe at the point where we have observed them for them to be there. Now, did that break cosmology? No, it didn't break anything. It's just, all right, well, we gotta repair some stuff that might have been wrong before. That's the continual way that we improve our theories of everything, not just physics, of any theory. Are there black holes inside of those little red dots? I don't know because we don't know what they are right now. Are they galaxies? Are they are they the first galaxies that we've ever observed? We think so. Are they gigantic stars that were able to form because the universe was so much smaller, and so they were able to collect a lot more dust than they're able to now? If they're stars that are that big, yes, they would form black holes. Are there black holes inside of those little red dots as we observe them now? I don't know, because the James Webb Space Telescope has just seen them. So what you're touching on is a brand new observation that will probably go down in history as one of the pivotal observational moments and a gigantic kink in our theories of our understanding of how the early universe was being made. Are they black holes? Maybe. Are they stars? Maybe. Are they the earliest, youngest galaxies that ever formed, and they formed sooner than we thought that they could? Probably. I'm going to go with that one. Because if they're galaxies, then they definitely have black holes in them. If they're stars that have black holes in them, I don't have an explanation for that. But if they're galaxies that have black holes in them, I am totally on board. I just don't quite know for sure. And not even the people who made the James Webb Space Telescope are sure. You want to know how? I talked to them. I don't get paid nearly as much as they do, but I talked to them, and they told me some very interesting things. I don't know of a better question to end on than that one right there. So everybody, one more round of applause.